Hello guys, welcome to Telecom and AI. In this series, we are going on a complete journey through one of the most fundamental concepts in 5G NR, the resource grid. By the end of all four parts, you will understand how 5G organizes its spectrum, from resource block and numerologies to the mysterious point A, and finally to bandwidth parts and physical and virtual resource blocks. Whether you are studying for a 3GPP exam, working in telecom sector, or just curious about 5G internals, this series is for you. Let's get started. Welcome to part 1. This part asks a simple question. When a 5G base station transmits, how do hundreds of users share the spectrum simultaneously without stepping on each other? The answer starts with resource blocks. By the end of this part, you will know exactly what a resource block is. How does 5G's flexible numerologies change its bandwidth? And why 5G had to redesign the resource grid from ground up compared to LTE. Why do we need a resource grid? Imagine you are running a busy motorway system. You have multiple lanes, traffic lights, and different types of vehicles all sharing the same road. In 5G, we face an identical challenge. How do we organize the radio waves so that thousands of users can share the same spectrum without crashing into each other? The answer is resource grid. The resource grid is a structured, two-dimensional framework where the horizontal axis is time domain and then the vertical axis is frequency. By slicing the spectrum into small, precisely defined cells, the network can assign different cells and different radio waves to different users. So each user gets their own piece of the radio wave even if they are sharing the same carrier. Before diving into 5G, let's quickly recall 4G LTE. A 4G resource block is a two-dimensional object. For normal cyclic prefix, there are 12 subcarriers in frequency domain and 7 OFDM symbols in the time domain. For extended cyclic prefix, there are 12 subcarriers in the frequency domain and 6 OFDM symbols in the time domain in a single resource block. So the total bandwidth is fixed at 180 kHz. This was clean and simple, and it served the mobile broadband brilliantly. But 4G's rigidity became a problem when it came to 5G. 5G needed to handle not only smartphones but also industrial sensors, which would need, say, microsecond latency, and it also had to handle IoT devices on battery power for years, in addition to millimeter wave band. So one size could not truly fit all, which is why 5G introduced the concept of numerologies. Here is the single most important shift from 4G to 5G. In 5G, a resource block is defined only in the frequency domain. It always has 12 subcarriers in the frequency domain. But the subcarrier spacing is no longer fixed. Look at these two columns, one with numerology 0 with 15 kHz subcarrier spacing and one with numerology 1 and 30 kHz subcarrier spacing. Both of them have 12 subcarriers in the frequency domain. So each of these corresponds to one individual resource block. But because the spacing is doubled in numerology 1, the total bandwidth per resource block is also doubled. So for this numerology 0 with 15 kHz subcarrier spacing, the total bandwidth that is occupied by this resource block is 12 into 15 kHz, which corresponds to 180 kHz per resource block. On the other hand, for this mu equal to 130 kHz subcarrier spacing, the total bandwidth of this resource block for one resource block is 30 kHz into 12, which is equal to 360 kHz per resource block. So that is almost double as that of mu 0. Thus, there are same number of resource block for each of these numerologies, but then each block is wider. So the resource block covers more spectrum. So this is exactly why 5G can serve everything from narrow IoT channels to wide millimeter wave carriers with one unified resource grid framework. Now let me quickly walk you through the numerology table. Mu equal to 0 gives us the familiar 15 kilohertz subcarrier spacing, same as an LTE, with a resource block bandwidth of 180 kilohertz. As we increase the numerology, the subcarrier spacing doubles each time. Mu equal to 1 is 30 kilohertz. So this is actually the most common numerology used in 5G deployments in the 3.5 gigahertz band. Mu equal to 2 is 60 kilohertz, mu equal to 3 is 120 kilohertz, and so on and so forth. Thus, the resource block bandwidth in 5G goes from 180 kilohertz for 15 kilohertz subcarrier spacing till 2.88 megahertz for 240 kilohertz bandwidth in 240 kilohertz subcarrier spacing in FR2. Remember, the number of subcarriers per resource block is the same, equal to 12 for any of these subcarrier spacing. Now you might ask, so why would you want these different subcarrier spacing? The answer comes to the three main use cases of 5G, which we have discussed over and over in almost all of our previous videos. There is enhanced mobile broadband use case, there is low latency communication, and massive machine type communication, which involves thousands of sensors per 1 unit of a 5G cell. So since 5G has to support different use cases, it needed to use different numerologies, different subcarrier spacing in each of the frequency bands, and thus they are these engineering choices that are optimized for different use cases. Now let us finally take a look at the resource grid. So this is an accurate diagram of a 5G resource grid. The vertical axis is frequency, and then the x-axis is time domain. The fundamental unit of a resource grid is a resource element. One resource element corresponds to one subcarrier in frequency domain and one symbol in time domain. Remember, a 5G resource block is defined entirely within the frequency domain. It does not have any fixed symbol definition in the time domain. So here you can see two resource blocks in this resource grid. There is RB0 and then RB1. Each resource block occupies 12 subcarriers in the frequency domain. A natural question at this point is, how many resource blocks fit in a single 5G carrier? The answer depends on two things: the channel bandwidth and the numerology. For a 100 megahertz carrier with 30 kilohertz subcarrier spacing, that is numerology equal to 1, the standard allocates around 273 resource blocks. That's 100 megahertz divided by 30 kilohertz divided by 12 subcarriers. So the total amounts to around 273 resource blocks for 30 kilohertz. The rest of the resource blocks are used for guard bands. Similarly, for mu equal to 2, that is 60 kilohertz subcarrier spacing, the usable number of resource blocks that the standard defines is 135. Similar to the mu equal to 1, the rest of the resource blocks are used for guard bands. Thus, more resource blocks doesn't actually equal to more bandwidth, because in both cases the bandwidth of the channel, bandwidth of the that's allocated to the UE remains the same at 100 megahertz. But since the numerology is different, since the subcarrier spacing is different, the number of usable resource blocks differs. Now let us put 4G and 5G side by side. Both uses 12 subcarriers per resource blocks. That's one constant. Both uses OFDM, but almost everything else is different. 4G has a fixed 15 kilohertz subcarrier spacing, whereas 5G supports subcarrier spacing from 15 kilohertz to 240 kilohertz in FR2. 4G defines the resource block in both frequency and time domain, whereas for 5G this is defined only in frequency domain. The resource block bandwidth for 4G is fixed at 180 kHz, whereas for 5G it varies from 180 kHz to 2.88 MHz based on the subcarrier spacing that is used. The maximum number of resource blocks per carrier is fixed at like around 100 for 4G, whereas this can go up to 273 for 5G. The use cases for 4G and 5G differs as well. Now let us consolidate part 1 of this series. Resource blocks are the fundamental unit of spectrum allocation in 5G NR. They always consist of 12 subcarriers, unlike in the 4G where they are defined in both frequency and time domain. So in 5G, a resource block is defined only in the frequency domain. The subcarrier spacing, the numerology, determines the bandwidth of each resource block ranging from 180 kHz at 15 kHz subcarrier spacing all the way till 2.88 MHz at 240 kHz subcarrier spacing. So this flexibility is what allows 5G to simultaneously serve broadband users, ultra low latency communication and massive machine type communication. In part 2 of this series, we will answer the next big question. Where does this resource block grid actually begin? So that's where common resource blocks and the concept of point A comes into picture. Thanks for watching, and hope to see you in the next video where I'll explain in detail what exactly is a common resource block and how to find out where the common resource block begins and what exactly is point A. Bye bye.